All right, so we're going to do the notes today. I hope you guys had a nice 3-day weekend. All right, so here we go. Work on energy, conservation of energy. Okay, so simply, energy is the ability to perform work. If you want to do work, you need energy. All right, think about it. If you want to do anything in life, you need food. Food is energy. We know energy comes in various different forms. We have light energy, sound energy, mechanical, electrical, chemical energy, food energy. Energy is always able to change from one form to the other. However, the total energy will remain constant. Right? You eat food, it comes in the form of one energy that's like stored energy and chemical bonds, and then you use it in some form or other in your body, and it changes from one form to the other. And just like work, energy is measured in joules. Okay. When an object has net work done to it, so there is an overall work being done on the object has to accelerate. We know this because work is force times distance. If you apply a force, it's accelerating. So we also know that it accelerates in the same direction as the net work. And what happens is you are changing the object's kinetic energy. We're going to talk about that in a second. But work is basically defined as a change in kinetic energy. So here are your forms of energy. Now, we're going to talk about just three. The first one is kinetic energy. That is the energy of motion, right? It's based on mass and velocity, and the formula is right there. So a thing to note about this formula is that the mass is raised to the first power, right? Nothing, but V is squared. That means the velocity has a greater effect than the mass on the object. Right, so there's a question in your notes that says, why did baseball players cork their bats? So why did they cork their bats? If a baseball player corks their bat, their mass of the bat goes down, right? Even though you would think that would lower the kinetic energy. When the mass goes down, the ball player is able to swing the bat faster. And since the velocity goes up, the velocity has a greater impact on the overall kinetic energy. And basically, they can swing the bat much faster and provide much more greater kinetic energy from the bat to the ball. So that's why baseball players would cork their bats. Right? That's why professional ball players are not allowed to use aluminum bats. The wood bat weighs enough that they can't swing it as fast. If they had an aluminum bat, they would be able to swing the bat extremely quickly, and basically every ball, if they were to make contact, would be probably a home run or something like that, and would take away from the sport of the game. Right. The other two forms are potential, and that's being stored for something later. Right now, there's a ton of different types of potential energy. We're going to focus on two. Gravitational potential energy, that's affected by basically how high in the air the object is, right? And then elastic potential energy, or the energy stored in a spring. And then both formulas are provided. MGH for potential energy due to gravity, and then 1/2 kT squared for energy due to elasticity. Okay, so overall, the energy in the universe is constant, right? That is a law, a fact. When we're looking at these problems, we're going to define them in two ways. The system, that's what's happening in the problem itself, and then the surroundings, that is everything else. So we're going to look at two types, closed systems and open systems. In a closed system, right, the system is what's happening inside my hand, right? No energy is leaking in and no energy is leaking out. So the overall energy within this little system here remains constant the entire time. So the energy before is equal to the energy after, right? And then that's what this equation at the bottom states. So let's try this. Andrew is jumping off, has about 60 kilograms, and he jumps off of a diving board that's 0.3 meters, or that flexes 0.3 meters and has a stiffness of 2,200 newtons per meter. Two questions. How high in the air does Andrew get? And then how fast is he moving right before he hits the water? Okay. So when I look at these problems, the first thing I want to do is I want to look at, hey, what energy is going to be being used when the problem starts or initially, and then what energy do we have at the end of the problem or the part we're looking at? So right now we're looking at how high in the air does Andrew get. So initially we are on the ground. So let's think this through, right? If we're on the ground, we have no potential energy due to gravity because our height is 0, right? So this P, E, G does not exist. Okay, plus he's on a diving board. Now they're telling us a diving board flexes, so that would mean there is some potential energy due to elasticity. Okay, plus the other one would be kinetic energy. Let's think this through. The problem doesn't give us anything about Andrew's initial energy. In fact, we basically can determine that all of Andrew's initial energy is coming from this elastic part, nothing from kinetic either, so this goes away. So initially, all we have is potential energy due to elasticity. All right, now, the problem ends when we're trying to find out how high in the air does Andrew get. So when we're in the air, we're trying to find out how high he gets. Well, that means there's going to be a height, there is going to be potential energy due to gravity. Okay. Plus, we did PEE next. Well, if he's in the air, he is no longer on the diving board. So the diving board, even if it's still doing its thing, the diving board is not providing any energy to Andrew. Therefore, PEE, no need. And then kinetic energy. Well, where are we? We're at Andrew's highest point. As always, if you're at your highest point, your velocity has to be 0. If your velocity is 0, you have no kinetic energy. So really, this problem shrinks down to initially it's elastic potential energy, and it all gets converted to potential energy due to gravity. Okay? So now we can solve. This is 1/2 K, which is 22,000, times D squared. And on the other side, it's PEG, okay? That's mass, gravity, and then height, right? So if we solve for this, right, on the left side, when we solve for everything, we get 990. And then we divide it by everything on the right-hand side. Whoops. Divided by 60. You get 1.68 meters. Okay. So that's how high in the air Andrew got, 1.68 meters. That's part 1. So now let's look at part 2. We're going to do it the same way. I'm just going to write down this 1.68 meters as a reminder. All right, how fast is he moving right before he hits the water? We're going to tackle it the same way. Part 1 was from the diving board to his highest point. Part 2, highest point back to the water. Whenever we've done one of these problems, these two-parters, the final values always become the initial values. So if we think back, the only energy available to us at the end of part 1 was potential energy due to gravity. And we know the value was 990. We just solved for it. Okay. Now, when he hits the water, all right, let's think backwards. If he hits the water, his height is 0. That means there's no potential energy due to gravity. So this doesn't exist. When he hits the water, he's not hitting the diving board, thank goodness. So there's no elastic potential energy. That means it's all kinetic. So we can say 990 equals 1/2 m v squared. Okay. So now we solve for that. So that's 990. Right, 990 divided by 30, because that's half of 60, is 33, and you take the square root of 33, and it's 5.74. Oh, there you go. All right, so again, always, easiest way to do this, in my opinion, start with figuring out what energy do you have initially, what energy do you have at the end, and then make the problem much easier, much shorter, and then solve from there. So this was a closed system. The other types of problems are considered open systems, and that means work is being done to the system. Either the system is gaining energy from the outside, it's positive work, or it's losing energy to the outside, that would be negative work. So we have a skier, starts and rests at the top of an icy incline, 20 meters in the air. On the way down, friction does 500 joules of work against the person. How fast is the skier going at the bottom of the hill? Okay, so we'll do it like this, same way we did it before. In the beginning, the skier is at the top of a hill, so they have potential energy due to gravity. All right, nothing on this problem talks about springs, rubber bands, so there is no elastic potential energy. What about kinetic energy? Well, the beginning of the problem says skier starts from rest, so Ke does not exist. Okay. However, there is a fourth energy we have to look at here initially, and that is friction. So friction is 500. Now let's think this through. Is friction going to do work to the system that's going to increase the overall energy of the system, or would friction do work to the system that's going to decrease the overall energy of the system? And we know friction always works against us, right? So friction is going to take away, it is negative work, so we're going to do minus 500. This is energy due to friction, you could say. Okay. At the end of the problem, the skier, we want to know how fast is the skier going, and they're at the bottom of the hill. Well, if they're at the bottom of the hill, potential energy due to gravity is also going to be 0. We know there's no elastic energy at all, so all the energy at the end has to be kinetic. Right? And now we can basically plug everything in. So 89.8 times 20 minus 500 equals 1/2 80 V squared. Okay, so 80 times 9.8 times 20, right? This is 15,680 minus 500, all right, equals 40 V squared. So 15,680 minus 500, right? That's 15,180. Divide that by 40, and then that's 379. Oh, don't spin that yet. And then take the square root. I got 19.48. We'll just round that. So the skier is moving at roughly 19.5 meters per second. Okay. Same way as we did the closed system. The only difference is initially we looked at this last set of work. We said it's friction. Well, the problem says it's friction. Because it's friction, we know friction is a negative work because it's going to take work away from the system. It's doing negative work to the system. So that's why it's minus 500. Okay. And then that became the initial setup. And then after that, it was the same as the closed system. Right. I hope you guys have a good day. We're going to do some more practice with this stuff tomorrow. And I will see you guys later.